promised to show in the last video that fyy as evaluated at the collinear points is always negative. Now I mentioned that doing this algebraically is difficult, so instead we do it numerically. To do it numerically, we need to evaluate fyy for all values of mu ranging from 0 to 0.5. However, there's a small problem in that this equation depends not only on mu but also on Lx, which is the x location, the x coordinate of the collinear point. That means that for each mu, we need to solve for the 3 collinear points and then evaluate fyy 3 times for each of the collinear points and show that each of those evaluations for all mu is negative. To start with, we need an equation for Lx, and we have that from our previous set of notes. At the very end, we came up with this equation, which is the equation for equilibrium points when y is 0. So we need to non-dimensionalize this. Let's go ahead and write it down. So to non-dimensionalize this, we'll start by non-dimensionalizing the length. So we're going to pull L out of here, and I'm also going to replace x1 with mu and x2 with 1 minus mu, and I'm also going to replace theta dot squared with 1. So we're essentially non-dimensionalizing both time and length at the same time. So that's going to give us, so now we're going to divide through by L so that this x is by itself, and we end up, oops, I forgot there's an L squared over here. We're going to end up with g over L cubed on this side plus x. Now remember from our discussion of non-dimensionalization that we determined that g over L cubed is equal to 1 over m1 plus m2. So here you can see this is going to become 1 over m1 plus m2, and we have m1 over that. That's equal to 1 minus mu. And then, whoops, that should be m2, not m squared. So this is going to give us m2 over m1 plus m2, which is simply mu. So now for each mu, we need to evaluate this equation for 3 roots, and then plug each of those roots back in here and evaluate fyy 3 times. So essentially we're going to see a plot that's going to look like 3 curves, and we're going to see that they're all below 0. So let's go on over into Python to finish this up. Let's start by coding up Lx. It's going to depend on x and mu, and it's going to look like this. So we're going to want to evaluate this for a couple of roots, and for that we're going to import from SciPy a function called root scalar. And I'm going to make a function that's going to return to us the root that corresponds to L1, and it's going to be a function of mu. So for this, we're going to call root scalar, and for the function, of course, we give it Lx. For the args, we give it mu. We're going to leave the method as none, but for bracket, here, this function, this root scalar function, expects a range that has a 0 in it. It expects a range where one end is positive and the other is negative, or vice versa. So we need to give this some value. Because it's the L1 root, we need to give it some value slightly greater than negative mu and slightly less than 1 minus mu. So for that we're going to need some kind of epsilon, and for that we'll use numpy. So now for our bracket we can say negative mu plus epsilon to 1 minus mu minus epsilon. And so now that should give us, this function should give us the value of the L1 point, non-dimensionalized of course. Let's double check this real quick. We're going to run the code, which is going to bring these functions into our workspace, and we're going to check the value of this L1 function for the value of mu. This is about the value of mu for the Earth-Moon system, and this should give us a value of about 0.83. And okay, so it does work, but as we see, this is returning an object, and I want it to return a value, so we'll just make sure it returns the root value. So if we do that again, okay, perfect. So let's copy this for L1 and L2, or L2 and L3. The bracket for L2, we want it to go from slightly above 1 minus mu, and we want it to go far enough out, and I think 2 is probably a good value for there. Similarly for L3, we want it to start from rather far out, and we want it to go up to negative mu minus epsilon, right? Because it's going to be on towards the negative side of the primary body. So let's go ahead and run that and double check our values for the Earth-Moon system. So for L2, we should see something just above 1, right? And for L3, we should see something just below negative 1, right? So that's what we get. Okay. Now let's also code up FYY. And we're going to treat this as a function of both mu and Lx. So for each value of mu, we're going to compute L1, L2, L3, and then we'll evaluate FYY 3 times. And we'll store those values and then plot them. So this is going to look like, okay, so now let's prep things for evaluating over a large range of mu's. We're going to want to store all these evaluated values. And for our range, let's use the linspace function to create an even range between epsilon and 0.5, and we'll make 1,000 of these. So for each mu in the range, we're going to compute FYY for the value of mu and for L1 at that value of mu, and we'll append that to FYY1. And we'll go ahead and copy this for L2 and L3. And let's run this real quick and just make sure that we don't have any glaring issues. Okay, it runs, cool. Now let's go ahead and plot this. I'll make sure that the L1 value is blue and that the other two values are distinct colors. So we'll make the L2 value red and the L3 value green. So let's go ahead and run this and see what we get. So, okay, let's quickly add a grid just so it looks a little bit easier to look at. So we can see right away that the blue line, which represents Lagrange point 1, that's always negative, and that's what we were setting out to prove here, is that FYY is negative for all values of mu. The red one as well, that's Lagrange point 2, we can see that that's also always negative. For L3, it looks like it's mostly negative, but it's starting very close to 0, and it's not clear from this graph if it's going to be above 0, what it's going to look like for those very small values of mu. So let's take a look at the first few values here. So the first value is positive, and the second one is negative. Let's take a look at what the mu values are in that range. So we go from our epsilon value, minus 16th, all the way to 5e to the minus 4, which is fairly large because Sun-Earth mu, for example, is 3 to the minus 6th. So we'll want to take a closer look here. And so to do that, we're going to change our range, and we're going to evaluate from epsilon to epsilon times 1,000. And let's take a look at what this gives us. So we can see the red line here is always negative. That's something that was worth taking a look at just to make sure that that one did stay negative. Let's quickly check that the blue line is down there as well. Yep, that's the case. And let's go ahead and remove that plot so we can see just the green line. So we can see at the very start we have this sort of like back and forth. And from my experience, when you see something like that, that's due to errors in machine precision. So here we're basically just seeing a bunch of round off errors and it's not clear what we're getting. But as we move on, we are clearly in negative territory. And for these mu values, 1e to the minus 13th, these are very, very small mu values. So we can rest assured that for any purpose that we'd be interested in, this value is always going to be negative. To give some context, the Ceres system, Ceres Sun system, Ceres is the dwarf planet in the asteroid belt, the mu of that system is on the order of e to the minus 10th. So you can see that e to the minus 13th is extremely low. So essentially, we set out to show that fyy is always negative. We couldn't show it algebraically, so instead we were able to show it numerically, because for all values of mu and for all values of Lx, fyy for all of the collinear points is always negative.